This is the final demo video for Group 14. Our project is called ROAM, Robotic Observer of Abandoned Materials. This was designed and put together by Daniel Clausen, who is responsible for the computer vision hardware and software, Claire Persinger, who is responsible for the PCB and hardware, Nathan Little, who's responsible for the robotic guidance and web development, as well as Ethan Robotham on systems integration and communication. Our project, ROAM, is an autonomously driving robot. It records items on the sidewalks and reports them to a user interface website. In this presentation, we aim to show the final demonstration of our key engineering specifications, as well as design and testing challenges that we have faced along the way.
ROAM is an autonomous sidewalk traversing robot designed to identify and report trash and treasure items in real time. Its architecture is built from several tightly integrated subsystems, each with a specific role. At the top of the system is the Raspberry Pi 5, which acts as a high-level brain. The Pi handles all the computational heavy tasks using LiDAR-based navigation, sidewalk following, and YOLO object detection. Whether the Pi identifies something or it needs to steer, it simply sends a JSON to the microcontroller. Those messages go to the ESP32S3. The ESP32 is responsible for reading commands from the Pi, generating precise PWM signals for the motors, driving the OLED display, and controlling LEDs and status indicators. It also multitasks. One core handles the motor and UART communication, while the other core manages the cellular modem. For long-range communication, we use the SIM7600 G-H module. It provides two critical functions: GPS, which gives an accurate position fix for every detected item, and two, cellular data, which uploads those coordinates to our website using HTTP POST requests. This lets ROAM operate anywhere outdoors without relying on Wi-Fi. All these parts are connected through a set of custom PCBs, which are designed specifically for this project. These boards handle power regulation, level shifting, SIM7600 power control, motor driver interfacing, and sensor breakouts. The power distribution system converts our 12-volt battery into clean, regulated 5-volt and 3.3 rails for the Pi, ESP32, sensors, and modem. For movement, ROAM uses two high-torque DC gear motors driven by a dual-channel BTS 7960 motor driver. Differential steering allows the robot to turn smoothly and compensate for sidewalk curvature. The motor driver receives a PWM from the ESP32 and translates it into wheel torque. On the perception side, we use LiDAR for navigation and a camera for object classification. LiDAR helps the Pi keep the robot centered on sidewalk and avoid obstacles, while YOLO identifies trash and treasure items for logging. Finally, everything connects to our Flash-based website, which plots the robot's GPS uploads on a live, interactive map and stores log for analysis. Together, these subsystems form a fully autonomous, cloud-connected robot platform capable of navigating sidewalks, recognizing objects, and reporting them in real time.
Some of our engineering specifications that we will demo in these videos are our treasure identification accuracy, which we aim to have as above 70%, our object treasure detection range, which we want to be between 0.5 meters and 3 meters, and our autonomous driving, which we aim to make it 25 feet without going out of bounds.
The first key specification is keeping identification accuracy above 70% on average. Footage of one of our trials measuring the identification accuracy by manually pushing ROAM down the sidewalk and seeing how many objects it can identify. Here we see a table of all 10 trials measuring identification accuracy, averaging out to 79% accurate.
The second key specification is seeing objects from 0.5 meters to 3 meters away. This checks the detection range. This test shows that we're able to see objects at all specified ranges. We now move Roam away and back to check them again. This chart shows the success rate of 10 different objects at the specified ranges.
In demonstrating key engineering specification number 3, we are attempting to show off the autonomous driving that we've curated over the semester. Our goal is to move 25 feet and stay within the bounds of our walkway. So we're doing this by having our robot run down a hallway. In this video, you'll see us laying out a 25-foot tape measure so we're able to keep track of how far our robot is driving. And at the end of that 25 feet, we have our robot preset to stop based off of the distance and time that it takes. So you'll see that at the end of the video, it stops. As you can see in this video, we are getting ready to set up the robot and send it down this walkway and have it complete that 25 feet. We ran multiple versions of this test and we have had measurable success and additionally an amount of struggle that came with these tests. We continue to try to update and make our LiDAR system better, but we're still seeing it veer off its pathway.
Next, we'll demonstrate the full functionality of Roam. This includes driving down a pathway while identifying objects along the side of the path and uploading their classification to the website with GPS coordinate information. This information will also be used to light up LEDs and change an LCD screen on Roam itself.
In this video, you see one of our group mates holding the robot and pushing it out. And we pan to what the robot's camera is seeing. You can see it identifying objects as it's driving down this path. Then you can see us move over to our map view where we see it update treasure and trash that it had just seen in that video. And you can soon see us zooming into the location as we wait for more trash and treasure logs to come up as the robot keeps going down its path. So here you see us zooming into the location. So it's updating our website not only with the identification of those objects, but also the coordinates of those objects. And that, as you can see, is pinned to where we are because we're standing next to the robot. And the trash and treasure that it picked up is telling us there's things that we're able to come and collect. And now you can see it continuing its path and veering off the path, but you can see these pictures that it took along the way showing the confidence of the trash and treasure that it found. So they're all above mostly about 70%. There's a few that because it's dark, it didn't pick up very well, but in the fresh light of day, typically we are seeing a confidence level above 70%. So it's still showing some pictures from the live feed camera that you just saw. So in this clip, we are showing the LEDs on my MCU board. Right now, they're shining red and yellow before it was red and green, and red and yellow says trash. So it's showing us the trash that we're seeing on the camera. And we're going to turn the robot to where we have some furniture laid out. And you can see the LED turn green, meaning that it's seeing treasure, and you see it on the LCD screen. And you can also see it from the camera that the Pi has that it identified treasure. Thank you for watching.